So, good afternoon, everyone. Welcome to the week 8 of this tutorial session of the course Principles of Communication System. So, let me check whether this video is recording or not. Yeah, it's recording. So, today we will solve question based on the week 8, whatever is taught in the week 8 in the NPTEL portal of this course of Principles of Communication System. And after that, we will solve some of the questions, important questions related to that. And this video is also recorded and will be uploaded on YouTube. If you have any doubt, you can watch from the YouTube as well. So the first question is quantization is used to map the four options given. The first option is continuous time signal to discrete time signal, a continuous time aperiodic signal to a power signal, samples of continuous time signal to a discrete sets of values, and a random continuous time signal to a deterministic discrete time signal. So for this question, option C is correct. So quantization is used to map the samples of continuous time signal to a discrete sets of values. So actually quantization is used uh, like let's suppose this is our message signal. So here the sample can take any values. So mapping these samples to a discrete sets of values is termed as quantization. So here sample can take any values. So what does quantization do now? So the quantization, so this is a continuous sample that can take any continuous values. So here the quantization will help. So help in mapping these samples to a discrete sets of value. Mapping these samples to a discrete sets of values. So this is termed as quantization. So what is the purpose of quantization? So just the quantization purpose is to convert these samples to the information bits. So purpose of quantization is to convert a message signal to the information bits. So after this information bits, it can be transmitted or stored over the digital communication channel. So these information bits can be transmitted. I think my battery is little low, so I will keep it on charge. So these information bits can be transmitted or stored over the digital communication channel. So the first question is clear. So now we'll move on to the second question. The second question is based on the delta modulation. So in this question, it is asked in delta modulation, the distortion that occurs when the signal rises or falls rapidly in comparison to the reconstructed signal is termed as. So when the signal rises or falls rapidly, uh, the distortion occurs, and that distortion is seen while reconstructing the signal. So this distortion is termed as slope overload distortion. So it is termed as slope overload distortion. So second question is done. So we move on to the next question, the third one. So in this question, it is asking, consider a message signal MT with a spectrum MF. So MF is the Fourier transform of MT is MF, which is sampled with an ideal impulse train of sampling frequency Fs. So here sampling frequency is given Fs in this question. So sampling frequency is Fs here. So the spectrum of the resulting sampled signal is. So the spectrum of this signal is Fs summation n is equal to minus infinite to infinite m of f minus n Fs. So this will be the spectrum of this signal. Because we can see with the impulse, we can take an impulse train. So let's suppose impulse train is given as g of del t is equal to summation of n is equal to minus infinite to infinite del of t minus n ts. So this is the impulse train sampled at every ts frequency. So this is 0 ts minus ts 2ts minus 2ts, so on in the both the sides. So this is our impulse train, and let's suppose it is multiplied with the message signal mt. So this will be equal to summation of mt multiplied with summation of del of t minus n ts. So this can be also written as summation of mt. We can write like this. So the sample frequency can be written as n is equal to minus infinite to infinite m of n ts del of t minus n ts. So understood how we write this? We can write like this because whenever just I'm giving the situation mt multiplied del of t minus t naught, this can be written as m of t naught into del of t minus t naught. So because for the value of t is equal to t naught, the message signal will exist. So in that way, we can write like that. So the sampled message signal can be written like this. So now let's suppose we take the Fourier transform of mt. So this is become m of f. And also, so MT is G of del T into M of T. So when we take the Fourier transform MF, this will become G of del F convolution with M of F. Because if two signal in a time domain is in the multiplication form, so in the frequency domain it will be in the convolution form. So M of del F can be written as, so MF will be Fs k is equal to minus infinite to infinite convolution with del of F minus k into Fs. So now this can be written as Fs, and now this MF will exist only at KFS. So this convolution can be written as M of F minus K of Fs. Here K is equal to minus infinite to infinite. So this is written from this analogy like MF convolution with del of F minus F naught. This is equal to M of F minus F naught. So like this here in the question you can see the option is Fs M of F minus Ns. So substitute K to N. So we will get Fs N is equal to minus infinite to infinite M of F minus N Fs. Okay. So the correct answer for this question is option number C. So we'll move on to the next question. That is the question number 4. So in this question, it is asking a uniform quantizer with an odd number of quantization level is. So whenever the quantization level is, the number of quantization level is odd, that will be a mid-trend quantizer. We can see with the examples also. So let's suppose there is a uniform quantizer and there is 5 quantization interval. So 5 quantization interval means this is the first interval, second interval, third interval, fourth interval, and this is the fifth interval. So this will become minus 5 delta by 2. This is minus 3 delta by 2. This is minus delta by 2, 0 delta by 2, 3 delta by 2, and this is 5 delta by 2. Uh, my internet is not working, so I will just have one small recharge. So just give me 2 minutes. So here you can see there are 5 intervals. So it is a mid thread. Just give me 2 minutes. I will just have one recharge. Now let's suppose there is a sixth level of interval. Then so here in this question you can see There are six intervals: first, second, third, fourth, fifth, and sixth. So at the center, there is a mid rise. So this is mid rise for even number of quantization levels. Okay. Now for odd number of quantization level, this is mid trade. Okay, so the correct answer for this question is mid trade. Now what is the value? Like here it will be 2 delta minus 2 delta minus delta 0 delta and 2 delta. So if for mid trade quantizer we are looking what will be the value of quantization level. So if m is greater than or equal to 3 delta by 2 and less than 5 delta by 2, then the value of message signal will be 2 delta for the positive interval. Here you can see. Now if m is greater than or equal to delta by 2 and less than or equal to 3 delta by 2, then gm is equal to delta, and if m is greater than minus delta by 2 and less than delta by 2, the value of message signal is equal to 0. If the m lies between minus 3 delta by 2 to minus delta by 2, then gm is equal to minus delta, and if m lies between minus 5 delta by 2 to minus 3 delta by 2, then gm is equal to minus 2 delta. So similar question. The next question is the uniform quantizers with an even number of quantization level. So now here it is the even number of quantization level. So we have already studied. At the center it is a rise value you can see. So this is a mid-rise quantizer. So the correct answer is option number A. So for this also you can write the values for the different levels, what values it will take. So now we'll move on to the question number 6. So in question 6, it is given the message signal MT is equal to cos of 100 pi t. So it is asking what is the minimum sampling frequency required for no distortion. So aliasing occur when a message signal is sampled less than the Nyquist rate. So when does aliasing occurs? When the sampling frequency is less than the Nyquist rate, that is 2 of FM. For no distortion, Fs should be greater than equal to 2 of Fn. So this is also known as, at Fs is equal to 2 Fn, this is known as Nyquist rate. So when the message signal is sampled with greater than or equal to the Nyquist rate, then there is no aliasing occur and there is no distortion while recovering the signal at the demodulator end. So for this question, Fm is given as, here this is 100 pi. So 2 pi Fm is equal to 100 pi. So here Fm is equal to 50 hertz. So what should be the sampling frequency? That should be greater than equal to 2 into 50 hertz. So Fs is greater than equal to 100 hertz. So in this question it is asking what is the minimum sampling frequency required for no distortion. So that will be 100 hertz. So that is option number B is the correct answer for this question. So now we'll move on to the next question. That is question number 7. So in this question it is given, consider the sinusoidal message signal mt is equal to cos of 500 MIT. It is sampled using an impulse train with sampling frequency is given as 400 Hz, followed by the low pass filtering with an ideal low pass filter of cutoff frequency 500 Hz. What are the frequency of sinusoids present in the resulting signal? So for this question, mt is given as cos of 500 pi t. Okay. So what will be the spectrum of this signal? So mf, that is equal to half of del f minus 250 Hertz plus del of f plus 250 Hertz. Okay. Now it is sampled using a impulse train. So it is sampled using impulse train with sampling frequency fs is equal to 400 Hertz. So the sampled signal has a spectrum. So we have already seen what will be the spectrum of sampled signal. We have already seen in the first question. The spectrum of sampled signal is equal to fs summation n is equal to minus infinite to infinite m of f minus n fs. So this is the spectrum of the sample signal. So the spectrum of the sinusoidal signal when sampled using impulse train can be given as, we'll write all the frequency component present in this, and after that we will apply a low pass filter in this. So that will be del of f minus 250 Hertz plus del of f plus 250 Hertz. So this was the mf. Now we will uh, subtract 400 Hertz and add also. So del of f minus 650 Hertz plus del of f plus 650 Hertz. Now del of f minus 150 Hertz plus del of f plus 1050 Hertz plus del of f plus 550 Hertz plus del of f minus 1050 Hertz plus del of f minus 550 Hertz, and so on. These frequency components will be present. Okay. Now what we have done? We have sampled, like we have send this signal to the low pass filter, and the cutoff frequency of low pass filter is 500 Hertz. It's given in the question. So cutoff frequency of low pass filter is given as 500 Hertz. Okay. So now the component which is having less than 500 Hertz will be reconstructed. So this one, this this will be filtered out by low pass filter. This is again. So only, Here it is 1150 hertz. So this will be again, it will pass through the low pass filter. So these four frequency component will be only present in the final reconstructed signal. So that is del of f minus 250 hertz plus del of f plus 250 hertz plus del of f minus 150 hertz and plus del of f plus 150 hertz. So what are the frequency component present in the resulting signal? That is 150 hertz and 250 hertz. So option B is the correct answer for this question. So now we'll move on to the question number 8, that it is asking, consider a message signal MT that is band limited to frequency FM. The minimum sampling rate required to sample this signal to avoid spectral distortion is. So we have already studied minimum sampling rate required to avoid distortion or aliasing is the Nyquist rate. So that is Nyquist rate. So the sampling frequency should be greater than or equal to 2 FM. So minimum sampling rate is 2 of FM. Okay. Fs is equal to 2 of FM. Let's suppose this is the spectrum of message signal. This is FM. So in this case only the distortion will be avoided and this will be the minimum sampling rate, because now this is Fs. So this is again 2Fm. So Fs should be equal to 2 of Fm. Okay. So the correct answer is option number A, that is 2 of Fm. So we'll move on to the question number 9. So in this question it is given 18 voice signals are sampled uniformly and then time division multiplexed. The sampling operation used flat top samples with 3 microsecond duration. The multiplexing operation included provision for synchronization by adding an extra pulse of sufficient amplitude and also 3 microsecond duration. The highest frequency component of each voice signal is 4 kHz. Assuming a sampling at the Nyquist rate, calculate the approximate silence time between successive pulse of the multiplex signal. So, Fs is given here 8 kilohertz. Why? Because Fs is equal to 2 of Fm. So that is Nyquist rate. It is sampled at the Nyquist rate. Now the time period will be Ts is equal to 1 by Fs. So this will be 1 by 8 kilohertz. So time period will be 125 microsecond. So since there will be 18 voice pulses and 1 sync pulses, okay? So there are 18 voice pulses and 1 sync pulses. So total pulse are 90. The total time interval for a single pulse is total time interval for single pulse is equal to 125 by 19 microseconds. So this is equal to around 6.58 microsecond. The silence time between pulses is 3.58 microseconds since each pulse has duration of 3 microseconds. So it is given each pulse duration is given as 3 microseconds. So silence time will be total time minus pulse duration. So this is equal to 6.58 microsecond minus 3 microsecond. So that is equal to 3.58 microseconds. So option D is the correct answer for this question. So now we'll move on to the last question of the day. So that is a GSM multi-frame has 26 frames with each frame comprising of 8 time slots. So there are 156.25 bits per time slot. So each bit being 3.70 microsecond long. What is approximate duration of the GSM multi-frame? So the approximate duration that can be given as, let's suppose each bit being 3.70 microsecond long. So multiplied with the time slot for each bit was 156.25 bits per time slot into the total number of time slots are 8 and there are 26 frame in each time slots. So that we can write as 3.70 into 10 to the power of minus 6 into 156.25 into 8 into 26. So the final answer, when you multiply it, you will get 120 milliseconds. So the correct answer is option number A. So this video is recorded also and it will be uploaded on YouTube. If you face any difficulty, you can comment on YouTube comment box. We will answer your queries. So thank you everyone for attending today's lecture. So we'll meet on next Saturday at the same time. Thank you. So we'll close the lecture here only now and this video will be uploaded on the YouTube as well.